Hi, I'm Elizabeth Leonard, the Associate Director of Research and Development at AAAS Science. I'm joining you from Washington, D.C., and my colleague Dr. Lee is joining from the UK. While this session is recorded, we hope to continue a conversation with you at the booth via Twitter or email, and of course, next year in person. Without further ado, please allow me to introduce our speaker. Dr. Michael Lee is the editor of Science Robotics. Before becoming an editor, he conducted research at the Paul Scherrer Institute and at the University of Oxford. Mike?
Thanks, Elizabeth. I'm really excited today to talk to you all about robotics. So if I was there in person, I would usually ask these three questions. The first question would be by way of raising your hand, who owns a robot? Generally, a few hands would go up. I would pick on a couple of those people who put their hands up and ask them, what does the robot do? And generally, they would say it's a cleaning robot, a robot that vacuums your floor, right? The next question I'd ask is, well, is it any good at what it's meant to do? Varying answers, but it all sort of converges onto one response, and that's kind of. So why are robot vacuum cleaners, why do they kind of work? Well, they get trapped between furniture, they have appetite for loose cables, and they're not that comprehensive in their coverage. And one kind of funny comment I got was that it moves my furniture around, a kind of robot feng shui, if you will. How do we solve these problems? Well, we move the furniture. We can tidy up the floor, move any cables or loose items. So we can ensure the floor is clear, that the robot can access all these areas, and you can weigh down any furniture that you don't want moving around. Clearly, this isn't an ideal case. I do it on a daily basis to kind of run my robot, but we don't want to design our environments, our home for robots, right? We want to be able to work anywhere, and herein lies the problem. It's all about the environment. The household is not an ideal environment in so much that it's unstructured, which is the polite term for messy, right? And I think really it's the point I want to kind of get across in this talk is that the majority of robots we see today operate in structured environments, focused on well-defined tasks. An example I often give are industrial robots, robots in cages, and these robots here are building the cars that we use and drive. So really the goal is to set robots free, okay? For robots to be truly useful, we want them to operate in unstructured environments and often with high levels of autonomy. We don't want to be there to intervene. We want to get on with the task that we've set them. So how do we make better robots? First of all, robots need better information, and they get it through sensors and a variety of different sensing modalities. Once they have that information, they need to be able to process it and make smart decisions. So we need developments in software, artificial intelligence, and better computing platforms to execute these programs. So once a robot knows what to do, how does it do it? It needs developments in electromechanical engineering and actuators to achieve locomotion in clever ways to create robots that are agile and maneuverable. And often we need all of these developments to come together. As engineers, we talk about the full stack solutions, the different layers of a solution. You need devices, components, and systems to all come together. And within those kind of approaches and those areas of research, you need advances from basic material science, from computer science, systems engineering. Robotics is really an interdisciplinary research field. So if we achieve all those goals, what does that mean for your robot vacuum cleaner? Well, it means it'll have better robot path planning. It'll know how to cover the floors more comprehensively. It'll know where to avoid certain traps. It'll learn from its mistakes, and it'll be able to recognize furniture and keep it where it is. And related to that, the robot should be able to detect objects. It should know what a loose cable is, what a loose item is, and be able to avoid those, right? And finally, if it does get stuck in any way, it should have the ability to maneuver itself out of those kind of tricky situations. So I spoke a lot about the robots that exist today and very much how bad robot vacuum cleaners are. That's not what we're focused on at Science Robotics. What we're most excited about is the robots of the future. What will they look like? So that's what I'm going to share now. This is a soft robot, so a robot made of soft materials going through some pretty tricky environments. Here's some sticky paper. So these are environments which conventional robots may struggle with. And what these soft robots do is really leverage the ability of their material properties to get through all these kind of tricky environments. And this is a mission for the robot, let's say, is delivering a sensor for some tricky situations. This really illustrates what one benefit of soft robots, the ability to get through these really tight gaps where you think a conventional robot would really struggle to do that. And one of the great things about soft robots is the simplicity of design and the versatility of the different areas it can locomote and move in. We're also excited about robots which may not even be used on Earth. So for example, this is like a prototype of a Mars rover solving the problem of how do we get out of a kind of wet granular material such as wet sand. The trick here is not just to use your wheels and spin them, it's to use your legs and move your legs around to agitate this wet sand. You can see this a lot better in the next clip. And we're hoping these developments will end up being used in our future kind of Mars rovers for planetary exploration. In the same vein of legged robots, this is a robot I quite like, these quadruped robots or dog robots. And it's doing a really tricky thing here. And it's moving over a wet surface, which if you're a human is difficult, right? Let alone a machine. And it does this using a machine learning inspired controller, to be specific, a deep reinforcement learning to achieve locomotion in this very tricky environment. So you'll see in the next clip the robot moving without the controller, and you can see how it struggles. So straight off, you can see that it slipped in its back leg, and it's supported by cable, so it's not doing very well there at all. So that's what we're excited about as well, kind of combining developments in artificial intelligence with robotics. Another area we're excited about is undersea robots. This is a robot which is inspired by the natural world. It's a robot fish, which is designed to move and look like a real fish. The idea here is that we can develop these robots which can study these ecosystems, such as like the Great Barrier Reef, without disturbing the fish and other things surrounding it. In the bottom left, you'll see the video or the shot of the robot, and this is what the robot sees. And you can imagine that this would be deployed in many different scenarios, and we can get a better sense of what the ecology is and try to kind of learn from these missions. The next clip I'm going to show you is drones being used in the Antarctica, and this is a real. Next one's a real field mission where there should be real outcomes. right, thank you for your attention.